Hello, this is a continuation of the brief introduction to the Verilog HDL. I'm still using the slides of Professor Tamas Rajkovic from the Budapest University of Technology and Economics. So, yeah, let's continue. Implementing combinational logic. Wire-type signals can implement combinational logic only. Reg-type signals can implement both combinational and sequential logic. So when combinational logic is implemented using reg-type signals, the assignments must be evaluated when at least one input signal is changed. So like the sensitivity list needs to include one of the input signals. So, or a star character, for instance, at least one of the input signals should be included in sensitivity list, or a star character, which means any signal. So the keyword neg edge or pose edge isn't required in the sensitivity list. So this is neg edge. This specifies negative edge and positive edge of a signal, which is like a rising edge or falling edge of a signal. So this is not required. When combinational logic is implemented using reg-type signals, the always blocks must contain fully specified if and case instructions. If the if case instructions are not fully specified, latches will be inserted. So this will synthesize latches. So the synthesizer will create latches. And latches are not good components in digital logic in the context of chips and FPGAs. So the state of the reg-type signal is preserved by the latch when no assignment is made. So this is logical to insert a latch from the synthesizer, but this is not something we want. So for instance, here in this example, we have always at star, which is anything. If cell is 1, then reg signal equal in 0. But when cell is 0, reg signal is not going to be modified. So this is not a combinational circuit. This is a latch. This is a latch. And this is like a flip-flop with no clock. So it is a latch. So it's not a flip-flop. It's a latch. So this is wrong because if we are intending to generate a combinational function, then we will get a latch, and then the latch will create problems for us in the implementation. Latches are undesired. They implement asynchronous sequential logic and not combinational logic. When the if case instructions are fully specified, for instance, for the if all the else paths are present, for the case all possible alternatives are listed on or the default keyword is used, the result will be combinational logic. Example, a multiplexer. For instance, to describe a multiplexer, we use the else statement. So if cell is high, then reg signal is connected to in1. Else reg signal will be connected to in0. So this means that the if statement is fully specified. So this will not generate a latch. Only reg-type signals can implement sequential logic. Asynchronous latches must be avoided. Synchronous, flip-flops, and registers. Registers, they change their state at the rising or falling edge of the clock signal. The sensitivity list of the always block must contain the clock signal preceded by the pose edge for rising edge or the neg edge for falling edge keyword. So the pose edge or neg edge keyword. The if case instructions can be not fully specified. If so, the clock enable input of the flip-flops is used to prevent the state change when there is no assignment. Actually, it's better to have them fully specified because then you know what you are doing. If they are not fully specified, it means the cases that are not covered by your code, the flip-flop will not change its value. If it is that, if this is the behavior you want, then that's fine. If this is not the behavior you want, then you need to be careful about that. Implementing sequential logic. So here, when you see always at post edge of clock means any register that is inside this always block that is on the left hand side is going to be probably generated, synthesized as a flip-flop. So here, if RST, then the right signal receives 1B0. So this is synchronous reset, because reset is not part of the sensitivity list. So reset is a synchronous signal. Else, which is here, register load is a clock enable, or is like modification enable or load enable. So register signal receives the input. Data path components. So data path components, what is a data path? A data path is like you have in any sequential circuit, you have data modifiers that are controlled by a logic or a state machine. And this state machine is doing the control. So there is the data and the control. So data is implemented in the data path. And the data path components are data modifiers. So the most basic modifier is the adder. So addition, like regular addition, arithmetic addition. Use the plus operator. The result is 1 bit wider. MSB is the carry out. So for instance, right? So you have wire 15-0 AB sum and wire C in C out. You are assigning both a concatenation of signals. You are assigning them to the result of the addition. So the result of the addition will be sum plus carry. So carry is going to be on the left hand side because it is actually the MSB. And then on the right hand side of the expression, you have A plus B plus Cn, right? So this is an adder. So this adder is going to be determined depending on the values. It's going to be synthesized into a chain of full adders. Subtractor, use the minus operator. Very simple. So same thing. The result is 1 bit wider. MSB is the borrow out. No borrow input. There is no borrow input. Okay. Adder subtractor, wire AB. So you have here, you are making a selection between the subtraction and addition. You can do that, depending on a certain wire. So you can see that the A and B have 16 bits, which ranges from 0 to 15, and the result has 17 bits because there is one extra bit for the carry or the borrow, depending on whether you are doing a subtraction or an addition. A shifter. You can shift left or right, and shifting is very simple because it's just a concatenation of certain bits.
Sorry.
Yeah. So then the shift right, you are sending the data right. The shift left, you are sending the data left. And then you are padding with zeros. So this is 1 bit shift. You can do multiple bit shifts, and then it's going to be a different range. You can, like, if we do 2 bit shifts, we're going to do DN 50 and then 2B0 here instead of 1B0. Comparator. Use the rational operators A and B. Use the rational operators. ALT B, which means A less than B. A equal B. So the relational operators give a result of one wire, so 1 or 0. Multiplier, we can use the star operator. So this can be synthesized only if the FPGA contains multipliers. If it contains hardware multipliers, it means they are circuit already there in silicon that are doing multiplication. So you go to datasheet of FPGA, you find a lot of them. They are doing 18 by 19 multiplications. 18 bits multiplied by 18 or 18 by 19, depending on some of the implementations. Shift register example. So synchronous reset and load, bidirectional left and right shift. So the register is called SHR and the data is called DN, and reset, we have control wires, reset, load, direction, and serial in. So here we reset the shift register to 0, and then if we compare if load is asserted, then we load directly the parallel inputs into the shift registers. Else, if the direction is 1, then we are shifting to the right. So SHR will shifting by 1 position to the right, else we are shifting by 1 position to the left by using the serial in. So this is very simple coding. This is perfectly synthesizable. This is perfectly synthesizable code. So this kind of code where we are using, data path operators and, registers and always blocks with the pos edge or neg edge of the clock, right? It's called RTL, register transfer level. Any code that is not register transfer level, and we can write something like that, will not be synthesizable. So the synthesizer will not be able to transform it into a circuit. Counter. Example of counter, synchronous reset and load, bidirectional up-down counter. So here we can look at the counter. So the register of 9 bits that implement the count. The counter is called count. The parallel load is called DN. And then we have 3 control signals that are reset, load, and direction. So if reset, then count is initialized to 0. Else, if load is asserted, then count will be loaded with the values in the DN input. Else, if the direction is 1 is asserted, then it is counting down. So count receives count minus 1. Else, count receives count plus 1, which is counting up. So here you notice that the constant is 9 tick D1. So it means it is a 1 that is represented on 9 bits, which is the same size as the counter on 9 bits. So this is very important. If you put -1, it will work, but it defaults to 32. But it will take the maximum for the register. So it will transform it into 32 first, 32 bits, and then it will look like that count is 9 bits, and then it will transform it back to 9 bits automatically. So the compiler does that without any problem. However, it's better for clarity of the code so that you don't make any mistake to write it this way. And here we notice there is a TC, which is the counter up. So when the counter is up, so when we are counting down, the kind of carry happens when the value of count becomes 0. Otherwise, it happens when the value of count becomes 511, which is 2 to the power of 9 minus 1. Priority of the control signals. The value of the control inputs are examined in the order they are listed in the always block. The reset signal should have the highest priority, should be the first. Wrong logic may be synthesized if the order of the control inputs is not what the development tool expects. So, for instance, here, reset is evaluated first, then load, then enable. So this is what it is. In this case, reset is evaluated first, then enable, then load. Then if there is no enable, load is not going to be executed. So you can see that. This is important. If enable is not 1, then load is ignored. Like if enable is 0, load is ignored, right? Synchronous control signals have effect only at the rising or falling edge of the clock. The sensitivity list does not contain the synchronous control signals. We talked about that, like for instance, all the signals here are generated from flip-flop that is driven by the same clock. So they are synchronous. They are on the same clock domain. So they are synchronous. Being synchronous means there is no need to include the sensitivity list of for these signals inside the sensitivity list of the always block. The asynchronous control signals, they have an immediate effect. They are not synchronous to the clock. So the sensitivity list must contain the asynchronous control signals preceded with the post edge or next edge keyword. Actually, for FPGAs, all signals are synchronous. This is very rare. This is just for the reset block, because you have a reset block that is transforming the reset conditions into a synchronous reset signal that you're going to feed into your flip-flops. Finite state machines. Local parameters can be used to define the states. A register is required to store the current state. The case instruction can be used to select the current state. In each alternative, the if or case instructions can be used to check the value of the inputs and execute the proper state transition. Example, traffic light controller. 4 states: red, red, yellow, green, and yellow. An external timer generates the 1 clock cycle long enable signal. Okay. First implementation. The state register and the next state logic are in the same always block. User state encoding. Right? So local param state R is 2D0, state RY 2D1, state G is 2D2, and state Y is 2D3. Why 2 bits? Because we can represent 4 items using just 2 bits. So that's why the state register is 2 bits, 1, 0. Right? Always at pause edge of the clock. If reset, state is initialized to state red, red. Else, case, state. If it is red, then if we are allowed to change, then you go to red, yellow, right? Else, you stay in red. So next thing, if you are instead state red, yellow, if you are unable to change, you go to state green. Else, you stay in the same state. G, if enable, then you go to yellow. If you are in green, you go to yellow, and then otherwise you stay in green. If you are in yellow, you go to red. Else, you stay in yellow. So this is how we do it using the case. So here we are deriving wires, right? So these will drive the colors. So assign R, the wire R, is when the state is equal to red or state is equal to red, yellow. Y is when state is equal to yellow or state is equal to red, yellow. And G is only when state equal state G. Second implementation, the state register and the next state logic are in different always blocks. Use state encoding. Okay. So here, you have the current state and next state, 2 registers, but these two registers are not going to be synthesized into both synthesized into flip-flops. Here in the previous implementation, they were both synthesized into flip-flops, but here this is a flip-flop because it has pause edge of the clock. If reset, we initialize current state into red. Else, if enable, current state receives next state. And then what is next state, right? Next state is going to be a combinational circuit. A combinational circuit, if we are red, next state is red, yellow. If we are red, yellow, next state is green. If you are green, next state is yellow. If you are yellow, next state is red. Very simple. And then, this is the same. Driving the outputs is going to be the same. So the outputs are generated directly from the current state. So this is going to be a wire. This is not going to be, but it has to be a reg, declared as a reg, because it is part of an always block, as we have seen before. Third implementation. The third implementation is the state register and the next state logic are in different always blocks, output encoding the FSM encoding, which is called user, which is Xilinx specific. Xilinx is a company of FPGA company. Verilog directive disables the state encoding optimization for the state register. I don't want to teach you something that has to do with Xilinx, so but you know it's fine if we look at it. So this is FSM encoding. This is a directive, Xilinx directive. What does it mean? This is going to disable the state encoding. The only difference is, like, everything is the same. The only difference is here. Why? Because here you can see if we force the states to be 3 bits, right? Then it's easy to have 3 bits representing RGB, red, yellow, and green. RYG. So R is the first one. So here it's very easy. This FSM encoding user means you are disabling the optimization. Why? Because in 3 bits you can have 8 states, and then you are having here only 4 states, which means the compiler can try to optimize and reduce a bit for you, but you say no, don't reduce it. So this is what you are saying. But this is just valid for Xilinx. I don't know whether it's valid for Intel, but it's valid for Xilinx. Memories, RAMs and ROMs. Verilog description of the memories. Memories can be treated as one-dimensional array. So it has a width, number of bits in a data word, and it has number of words, number of data words in the memory. This value must be a power of 2. Memories store data, therefore the array must be declared as a register type. So this is a reg. Then you have the size of the register of one data word, size of one data word, and then you use whatever identifier you want to use. It doesn't have to be mem. You can use, you know, array one, whatever word, whatever name you want to give. And then here you are going to use to declare the dimension of the memory, which means the size of the memory or the number of words, copies of the same size word here. So Xilinx FPGAs contain 2 different memory resources, distributed RAM and block RAM. Same thing for the Intel. They contain distributed RAM and block RAM, the same thing. So distributed RAM, I'm not going to cover this in detail, but you know, distributed RAM is useful for storing small amount of data. For example, register file, 1 write port and 1 or 2 read ports. The address is shared between the write and the first read port. The address for the second read port can be different. Write is synchronous, read is asynchronous. What does asynchronous means? Means that you give the address, the data comes in the same clock cycle. Synchronous means you give the address and then you next rising edge of the clock, whatever you have address and data is going to be effectively written. Verilog description of the distributed RAM. So here, so this is very important. If you have a memory of 31.0, so which is 32 locations of 4 bits memory, and then you have the address is 5 bits, address A, address B, 2 address ports, and then you have the data in, which is 4 bits, and then the write enable, which is 1 wire signal. So always at post edge of the clock, if you have write enable, then the memory location at address A is going to be overwritten with DN. That's what it means, but at the positive edge. But read ports are, you are declaring them wire 30, the out A and the out B, So this is always going to be evaluated every time address A changes and address B changes, because they are defined like that. So you can use an assign statement. Here they are using a direct declaration. This is valid, but assign is better. So you can declare these up and use an assign statement. Assign the out A equal mem of address A, the out B equal mem of address B, right? Block RAM. 18 kilobit capacity per RAM block, different configurations, 16 by 1 bit, etc. So many configurations. Is the same thing for Altera or Intel. Yeah, dual port memory, 2 independent read-write ports, right? So clock data output reset, enable, write enable, etc. So they are doubled. Address input, data input, and data output. Write and read is synchronous. Write happens at the rising or falling edge of the clock when enable x equal 1 and WEX, or write enable EX equal 1. Read happens at the rising edge or falling edge of the clock when enable X equal 1. So this is a dual port. So 2 ports, right? So this is a single port and this is a dual port. This is single port memory, this is dual port. Verilog description of the block RAM. Example, 2K by 12-bit RAM with 1 write and 1 read ports. The RAM style block, so these are directives. So you are saying, I want to generate this as a RAM. So this is specific for Intel. Specific for Xilinx, not for Intel. So you can initialize the RAM contents via an external data file. You use read mem b and read mem h. So read mem b here and read mem h, they are Verilog directives. They are directives in Verilog that are going to load hexadecimal data and load it inside binary or hexadecimal. You know, binary data file or hexadecimal data file, depending whether you read mem b is for binary, read mem h is for hex. And then you are going to load a portion of it. So start address, end address. And then you're going to load that with the file that is in the same directory where your simulation is running. Initial blocks. What is an initial block? An initial block is a statement that is not synthesizable, that is useful for simulation. You say, at the beginning, do this. You know, initialize things as if you are writing a program, a sequential program, as if it is programming, but it's not hardware. This is used, so that's why they are saying cannot be used for implementing hardware components. The assignments in the initial block are evaluated at the beginning of the synthesis or the simulation. If, else, and case instructions can be used in initial blocks. Multiple statements can be grouped using begin and end keywords. Example, initializing the contents of the 2K by 12-bit RAM. So here you are declaring a bunch of signals, and now you are initializing the RAM. So you do initial read mem h, get all the contents of this data mem data hex.txt file, and put that in the instance mem, in the memory mem, that is the reg here. And after that, you can write the Verilog of the behavior of the memory. So memory is RAM and ROM. So a ROM is just a memory that is actually a case statement. So you can decide to create a ROM by just having an address and a wire, two wires, and then a series of muxes, and then you put constants assigned to them depending on the value of the address. This is a ROM. So without the right port, the distributed RAMs and the block RAMs can be also used as ROMs. So they are not ROMs at fabrication, but they are ROMs in terms of functionality. So they will behave as ROMs. So Verilog description of the distributed ROM. So this is a ROM. So this is the ROM. You are initializing the ROM, and you are just assigning the output with when the address changes, the output changes, and that's it. So there is no writing to it. So same thing for the block ROM, but this is actually clocked. So you see the things are happening inside the always block with the posage of the clock. Three-state drivers. What is the three-state driver? Like, three-state drivers are only available for the I/O pins of the FPGA device. Internal signals cannot be high impedance, cannot have tri-state inside. So Verilog description of three-state drivers: output pin, output wire 70, the out pin, and then you have the wire data out, and then output enable. So assign the out pin, you are using OE as the enabler. So you are selecting, if OE output enable is asserted, then data out is connected to the out pin. If output enable is not asserted, you use 8B ZZZZ. Z means high impedance. High impedance means there is no electricity going there. So it's a wire that is disconnected from the driver. It's disconnected from a driver. So any other wire that is connected to that wire from another side, outside of the output enable, right, can drive the signal in simulation. So another way is to do it bidirectional. So you have an in-out wire, and then you have a bidirectional pin. So this is assigning it as an output, and when it is when the output enable is disabled, then you can assign it also as an input. But you have to transform this bidirectional pin into data in and data out. So you don't use bidir pin in other assignments, you use data in and data out instead, right? After these statements. This will finish our second part of this presentation. Thank you very much for your attention, and enjoy the presentation, hopefully. Thanks.